To talk about like the motivations. My Linux kernel journey started with Android, getting involved in the Android rooting community. I think most people think of Android as like a mostly open mobile operating system, like in comparison to iOS, but that's not really the case, especially in the last 5 years or so for various reasons. Go ahead. Change the source. Screen share. Select that. No?
Just plug the HDMI cable.
Plug the. Yeah, I think so.
I'm really sorry for this. Okay, and the cable.
Okay, I'm really sorry, guys. I don't exactly know the situation, but it's fine. This is more of a dynamic talk anyway, so let's just talk. So like I said, my Linux kernel journey started with the Android rooting community, and so people have thought in the past that Android is kind of like an open mobile operating system in comparison to iOS. That's not necessarily true anymore in terms of like friendliness for rooting. Especially if you buy your device in the US because of like bootloader restrictions. So I got involved in Linux kernel exploitation that way. So throughout the course of this talk, you'll hear me compare a lot of things to the Android Sandbox. That's partially because of my experience, but also because Android is a really good example of an operating system that highly leverages Linux kernel sandboxing techniques for security. And in my opinion, they're doing it the best. And I think this is kind of evidenced in gray market exploit prices. And I also think that some people might view the topic of kernel sandboxing kind of dry. But I think that the topic becomes more compelling in the sense that put in the context of everyday security implications. And everyone in the room probably owns a cell phone. And so we all think, well, if I have to install an app from an untrusted source, how much would it take for an attacker to exploit it and gain root and put a rootkit on a device that has a camera, has a microphone, GPS system, and we carry everywhere? So I think more than one of us have, concerns about the security implications of that. So my involvement in Android got me started writing kernel exploits and got me thinking more about what the implications of a sandbox are. So what was happening for me is similar to what you might see with iOS, of like every time there's a kernel exploit or any exploit of any kind, people are rushing to the comments and say, hey, is this good for jailbreak, jailbreak, jailbreak? And so that happens to a much lesser extent on Android, but it still happens, and people were contacting me, asking me to write exploits for specific Linux kernel vulnerabilities, and I had to figure out like which ones were useful and which ones weren't. And figuring out what the security boundaries for that were, and how do we bypass them. I also wanted to get better at vulnerability research in general. I'm super sorry. Now this is actually my fault. More motivations for the talk. Since this talk is about finding exploitable bugs, I wanted to cover a little bit about the difference between exploit development and vulnerability research. Exploit development and vulnerability research are often used interchangeably because if you do one, you probably do the other to some extent, but they're different complementary skills. Exploit developers are responsible for the weaponization of a bug that might be theoretically exploitable, but exploit developers are kind of responsible for carrying it all the way through. And they're usually pretty good at recognizing whether it's realistically exploitable or only theoretical, and whether the location is accessible within an attack surface. Vulnerability research is more about code auditing, finding bugs themselves, tool building, like building fuzzers, and I would say both require a lot of the same skills. There's a lot of intersection, but they're different. Super sorry, I don't have, actually, since we don't have my screen, I'll just look at my notes here. Okay, so let's talk about what a sandbox actually is. For the purposes of the talk, I'm going to consider anything that places restrictions on a resource, on a process that a process can use via the operating system, a sandboxing technique. I also want to talk about containerization. There's some debate about whether containers constitute a security boundary. That can be a whole another talk in itself, but I'm not going to go down that route, but since containers are built on sandboxing primitives like namespaces, which themselves are kind of modern generalizations of CH roots, CH root jails, and since this perspective is this talk is from the perspective of me, an exploit developer, if I'm exploiting something that's running inside of a container that's preventing me from getting access to certain resources on the host, the container is a security boundary that I want to escape. So yes, containers are a security boundary from my perspective. And why should you care about sandbox escape bugs? I'm also really sorry that we don't have slides. This would have been a lot better if we did. I don't know what's going on, but I apologize. We're trying. So the type of bugs that are used to escape sandboxes have a higher security impact because they're going to work within more lockdown environments. Essentially, they have a larger impact because they work on most systems and environments. And even if you're not running inside of Sandbox,
I'm really sorry to
yeah,
interrupt. Do you have a way to ensure that this is something?
I can try. No, it's not detecting the HDMI at all. It's okay. I can just give the I can just give the talk.
Can I remove
Sure.
your
Yeah.
receiver?
Yeah. You can take out my UV key if you. Thank you. Yeah, let me keep going. The type of bugs that are used to escape sandboxes have a higher security impact because they're going to work within more lockdown environments. Essentially because they have a higher impact because they work on more systems and environments. Yeah, I have that too. It doesn't work. Yeah. I tried. We have all the physical adapters and the casting. I'm not exactly sure what's going on. Yeah, I'm not sure. I'm so sorry. But we can still talk. Let's talk. Okay. Even if you're not running inside a sandbox, these type of bugs tend to be more useful for various reasons. And I'll show some examples of that later. For one, you don't need to chain multiple bugs to access different resources if you have access to the entire kernel. that's it. And these bugs are generally easier to standardize with a generic exploit that works across different devices. The last part isn't always the case, but depending on the bug, it usually tends to be true. A little bit about basic operating system concepts. Unfortunately, I don't have my slides. I have a nice diagram here, but I wanted to really quickly introduce some basic concepts. System calls are the programming interface to services provided by the operating system, like resource allocation, memory, files, devices, basically everything. The kernel is responsible for deciding whether an untrusted application in Ring 3 is allowed to access a resource. So an application is going to get access to the kernel and run kernel code via system calls where an interrupt and execution is transferred to the kernel. So how are these sandbox boundaries enforced? When we attack a sandbox, we really need to understand what it protects against and how effective it is at enforcing the various restrictions it attempts to place on a sandbox process. It's possible to break these boundaries is a question that exploit developers and vulnerability researchers ask themselves, and ultimately the answer is yes, because untrusted processes still need some access to the kernel. The Linux kernel is a complex code base, low-level code written in C, and by default, it's going to have a lot of bugs. It's also huge. I think it's something like 30 million lines of code as of right now. And also, new kernel subsystems and redesigns introduce more reachable code from within sandboxes, and sometimes they break the assumptions of fundamental designs of sandboxing techniques, and we'll cover some examples of this later. We also want to think about things from the perspective of a developer. What kind of issues are there in implementing and maintaining these sandboxes and sandboxing layers, and where are there opportunities to break these boundaries? So again, the Linux kernel is a very, very large code base. Picking where to start can be difficult. Picking a target is a question of both reducing the subset of code that we focus on at one time, as well as trying to find more reachable code when we're running within a lockdown sandbox. And in order to find where we want to look for bugs in the kernel, we need to understand how the applicable sandbox techniques work and how these restrictions are enforced. I'm going to discuss the different ways sandboxing is implemented with respect to the kernel and what the remaining attack surface could look like, and various ways around them based on the inherent design of the sandboxing boundary. And as we go through, we can look at where some of the weaknesses may be in each one. Obviously, there are a lot of different types of sandboxing techniques for different types of applications, and different types of operating systems and stuff like that. And they all leverage some combination of the techniques that I'm going to talk about to differing degrees. The extent of these are used the extent that these are each used differ based on the configuration and specific use case. The first layer of sandboxing usually uses the traditional Linux file system permission model, which I'm sure you are all probably familiar with. It works by associating each system file with an owner and a group and assigning permission access rights for 3 different use cases: file owner, group, member, and everyone else. Linux capabilities are another layer. They allow the splitting of possible privileged kernel calls and services into groups of related functionality. That way, only a subset of capabilities of the process needs rights to be granted. This eliminates the need to give a process all rights. So you can kind of segment it. You can have an unprivileged process with access to a subset of privileged kernel calls, and this is sometimes how sandboxes create isolation between applications, where only one application is allowed to access a resource or a kernel service and controls access to the resource or other applications in user space. Namespaces also are another layer, especially in containers. They wrap a global system resource in an abstraction that makes it appear to the process within the namespace that they have their own isolated instance of the resource. Different types of namespaces are like network namespaces, which isolate stuff like network devices and ports, and user namespaces that isolate user and group IDs. And then SetComp filtering, which provides a means to filter which system calls are accessible to a process. And lastly, Linux security models, which implement like hooks in user level system calls where loaded security models are called into, and the function returns an access decision. So it was originally designed to implement mandatory access control modules such as like SELinux and AppArmor, but don't necessarily need to, but those are like the two most popular that are used. Just for the record, these methods are intended to reduce a reachable attack surface. They're not intended to provide any sort of like exploit mitigation or protection if a kernel vulnerability has been exploited. Even though some vendors might try to leverage them that way, that's not really their intended use. Some vendors try to use like trusted execution environments to protect some important kernel structures to prevent the disabling of security modules and isolation measures, but those can be bypassed easily, and by easily I mean by some like clever exploit engineering work. But in the end, we can assume that if a sandbox application can reach an exploitable kernel bug, then it's game over. So let's look at these methods individually and maybe examine some of their weaknesses. And the first one I'm going to cover is SetComp. So SetComp, like I said, provides a means to filter accessible system calls for a process. It's an interesting one because the main purpose is to reduce the kernel attack surface by limiting what system calls a process can access. And it has two modes: the original mode, the strict mode, that only allows a few system calls like read, write, and exit, and a BPF mode where filtering is done using a classic BPF program. But it has a few weaknesses. For one, it forces developers to think about what system calls their application is making rather than the actual resources that it accesses. And this can create compatibility issues. For example, libraries can get recompiled with new system calls that then they have to be specifically allowed. For example, there was a recent issue due to VDSO changes that started calling into like 64-bit time system calls that weren't allowed through most SetComp filters for 32-bit machines. And that caused a lot of applications to break or misbehave. That kind of thing happens a lot, and it kind of backs SetComp policy writers into a corner, into writing a deny list versus an allow list. And many ship with like automatically generated SetComp filters that only remove a few risky system calls. And actually, for example, Android does this by generating this SetComp filter programmatically and allowing system calls that are in their like libc library, which is called Bionic. And in this case, policies aren't really designed to be per application and only allows more coarse grain control. And this kind of defeats the purpose of limiting kernel code only to what a specific process might need. And the other thing is that SetComp is unable to do deep argument inspection to what is passed into system calls, and this is because pointers can't be dereferenced in classic BPF programs. So for example, a SetComp filter can't check a file path being passed to a system call to restrict what kind of files the system call can operate on. And remember, everything on Linux is a file. So file operations for different file types are handled by file operation functions that are defined in a structure. And if I had slides, you would be able to see it right now. And also, I'm going to show you an exploitable bug. Well, I would have showed you an exploitable bug that I found looking in a place that bypassed most sandboxing filters. I was reading a blog post and I got curious about how the file proc pibmem, proc self pibmem did file operations. And if you don't know, this file can be used to access the pages of a process's own virtual memory. And because it's providing access to its own memory, the file isn't restricted by DAC, and its file read-write operations are accessible to itself, like within a sandbox. And remember, everything on Linux is a file. So file operations for different files are handled by functions defined in a file operation structure, and you would be able to see it. And I would right now show you the actual bug. With the bugs that I show you, it's actually totally fine that we don't have code because it's not really that important about what the bug is. So you don't have to squint and see. There's nothing to see. So the bug that I found was in the actual read-write function implementation for procpidmem. And when you write to procpidmem, you end up where the bug is. And it was an integer type confusion that allowed for a buffer overflow because it ended up in a mem copy with no checks, but just trust me. Okay, so now I'm going to talk about SELinux, which is one of the type of Linux security models that implements mandatory access control Mac. It's not the only one, but it's the one Android uses, and the same ideas can kind of also apply to like other LSM Macs like AppArmor. And so every running process on a system with SELinux has something called an SELinux security context. Each context has a set of rules that dictate what it is allowed to do. The entire set of rules for every security context is defined by something called an SCLinux Policy, which is loaded into the kernel, usually by from a protected partition on disk. If well implemented, it should be. Access is checked inside of a hook of a system call. And an example, I had it on my slides, but you can't see it. But yes, it's implemented in a hook in the system call entry functions. So if something is not explicitly allowed access to a resource, it's denied. So SELinux has no concept of a super user. I might have mentioned before the example of Android, which uses SELinux sandboxing. Being a root user in a system with SELinux means very little because access is tightly controlled based on the security context, not the user. If you have a good policy, nothing should have almighty privileges, even a kernel context. Each policy rule has 4 components: a source context. I can't see. Can you? Yes, I will make the slides available afterwards, of course. Yeah, I don't know if somebody wants to help me fix the situation. I don't know what to do. Yeah, sure. Yeah, just tell me who to send it to. Are we getting something out of this with just me talking? Well, it's not quite follow along, but it's like it's different content, but yeah, we'll cover some of that. No, it was actually a different bug, but similar. I cover that bug later. Okay.
Export to a PowerPoint.
Okay.
We're just going to do a quick intermission here, guys. But the second half, we'll have slides. You're doing really great.
Totally fine. I don't mind. I'm just wondering if people are getting anything out of this without slides. But yes? Yes? Should we keep going? Should we keep going? Okay. All right, let's keep going. We got it?
Yes.
Okay.
Sending it twice was the charm, even though it's the same email.
Okay. Sure. And the PowerPoint, it has custom fonts. God damn it.
They should have fixed it in the export.
It's fine. It's fine.
It looks.
Yay! Thank you.
There's Windows source code on this.
It's safe with me. Okay. Awesome. Thank you so much for you guys' patience. We made it through all of this. I am proud of this diagram, though, so let's look at it for a second. No, it's fine. We are all the way here. Okay, so SELinux has no concept of a super user because it's tightly controlled if you have a good policy. And so this is an example, you can see now, of an SELinux denial being logged. Here the source context is shell. I think I was running an exploit from shell like ADB on the device, and the target context was netd, which is a network manager. Class is the other component, which is a Unix stream socket, and the permission was connect to. So I think I was trying from the shell to connect to a Unix socket that belonged to another process in the device, but because this was not explicitly allowed by the policy, it was denied. So you can kind of see how SELinux allows for finer granularity to access controls instead of only being able to specify who can read, write, or execute a file like in normal Linux file system permissions. It lets you specify who can unlink, append, move, specific file types, and specific security contexts and classes. So some of weaknesses of SELinux, it has both user space and kernel components that enforce policy. And because this is a kernel talk, I'm going to focus on kernel aspects. But it's important to be aware of the user space aspects because SELinux policy developers have to be aware of the various implementation details. SELinux policies are also extremely complex. This makes it hard to write scalable and maintainable policy. And because of this misconfigurations, sometimes out of convenience, are common. And of course, there have been implementation bugs that occur in the kernel as well. So some examples of how SELinux can fail and leave openings to reach exploitable bugs, not implementing granular control for new components. Your security is only good as your policy. So to configure an SE policy correctly, you have to give careful thought about what programs should have access to what and when a new component is introduced. So if you give an application or a resource with default security context that has all permissions enabled, SELinux, of course, is not going to be effective. This might sound trite, but this actually does happen. An example of this is like on Android Qualcomm devices where the neural processing unit driver that is used to do like AI machine learning operations was accessible to any untrusted app. And this driver, since it's used for like math, number crunching applications, it should be safe. But actually doesn't. It introduces the ripe attack surface. And a few of these bugs have been demonstrated in Android chains in the past year. And so this driver, after discovery of some of these bugs, was reported, has been locked down, but it's still accessible from some OEMs such as Samsung, US, Qualcomm devices. And another weakness of SELinux is that it doesn't work if there is not LSM security hooks in the system call or the reachable kernel code. And this was the case for bugs in like the perf system call that were used for sandbox escapes. And it's still the case for IOU Ring system calls. And I'm going to talk about that later. Another problem that can happen is the mishandling of capability checks in the kernel. And there have been several examples where LSM checks override capability checks in the kernel, which end up disabling entire runtime mitigations, or granting access to something that would otherwise be disallowed without SELinux, which SELinux is supposed to create more restrictions, right? So an example of this is an error with mmap min-adder, which dictates the lowest virtual address the memory map can reside at. And SELinux would actually override that capability, that Linux capability check, with administrators that could inadvertently allow unprivileged users to map at a null address. This actually happened in real life, not in theory, because wine programs needed to map at the null address. So administrators ended up allowing anyone to do that. There's also vulnerabilities in access checks functions, or have been, in implementations themselves. Like for example, SELinux function checking for send message on netlink sockets only checked the first message. So we could skip SELinux checks by putting a malicious message after a permitted one. There's also an opportunity to find vulnerabilities with policy gaps, such as these with like SELinux static analyzers. One of these tools is SELint, which is like used for SE policy managers, but you can use it offensively because it looks for convention violations, poor styles, and policies that could cause unexpected or insecure outcomes. For example, I could find file context labels that are associated with the wrong module. Another big one is namespaces. So namespaces is actually a really good way to isolate containerized applications into its own file system, process space, etc. But it does introduce some security problems, in particular with user namespaces. Oftentimes containers are configured such that containerized applications run with higher privileges in the container namespace than they would on the host or the main namespace. So an application running as root in the container namespace is not uncommon. And this is technically fine because they're restricted from accessing resources on the host, but there is more kernel attack surface that is accessible because more privileged kernel code is now reachable. This has an interesting side effect because now a whole subcategory of kernel bugs that have been previously dismissed as not having real security implications because the code is not unreachable can now be used to escape containers and sandboxes. Furthermore, creating a user namespace is now allowed from unprivileged by default in popular distributions. So they're useful for reaching privilege escalation bugs from outside a container too, just from unprivileged user running from whatever. A great example of this is a bug that my friend found contemporaneously with other people. This is a great example of user namespaces making more kernel code accessible because this bug would normally not be unreachable from unprivileged, but because they can use an unprivileged user can create a namespace. They're technically the root user in the namespace, so they can call this fsconfig system call. I'm kind of going to go fast here because I have a lot more stuff to cover. So now that we're somewhat familiar with what restrictions we need to deal with within a sandbox, let's talk about general places to look for bugs to be able to bypass these restrictions. General places to look: subsystems that don't necessarily perform privilege actions but run complex code. That's a good place to start. For example, IOU Ring, which I'm going to talk more about in a second, the Qualcomm NPU driver that I just discussed, and also well-sandbox environments compartmentalize responsibility for a resource so that only one process have access to it, and make it available to other processes via IPC. So that's another good place to look, in particular which files and what types of files are made accessible via the IPC mechanism and what permissions are given within a sandbox. On a system like Android, applications still need access to data from peripheral devices like camera, Bluetooth, etc. when using an app. And instead of allowing the application to talk directly to the device driver, it has a designated service process for each hardware component, which is the only one that's allowed to talk to that component. And in Android, that's done via binder. And bugs that are found there are super powerful because by design, every application must have access to it in order to do IPC. And as it turns out, there have been several sandbox escapable binder bugs that have been really good to do that. Another one is weird files and file system operations for unusual type of files. I already gave a couple of examples of these. I know you guys didn't get to see the code for them or the bugs, but I'll make the slides available. And system calls are kernel entry points with no LSM hooks. So the finely grained control of LSM loses its potency if you can't target somewhere that doesn't have hooks, right? So no access checks are really enforced there. IOU Ring is also a great example of this, which has further impact on sandboxing. And this isn't the case anymore, but for a long time, perf system calls didn't have LSM hooks either, and as you might guess, that was a great source of exploitable kernel sandbox escaping bugs. I will say, too, that when a new system call gets added, there's usually no LSM hooks to start, and they usually show up after years of kernel maintainers fighting with each other. So that's a good thing to keep in mind. So even though this talk is more general, I'm going to briefly discuss IOU Ring more in depth because I think it has important security implications. IOU Ring is a kernel subsystem that redefines how system calls are done in Linux by making asynchronous syscalls possible. Basically, system calls are dispatched from within the IOU Ring subsystem rather than entering directly via the normal system call interface. This is a performance-oriented thing, and it's useful for applications that are doing high-performance I/O. And so you've seen a big part of sandboxing is done via system calls filtering or hooks or restrictions. And so you can imagine how IOU Ring has the potential to disrupt the entire sandbox security model. So it has security implications for a number of reasons. For one, it can be used to effectively bypass SetComp entirely because SetComp does filtering on system call entry. So if you're doing the syscall via IOU Ring and it dispatches it, the system call can't be filtered or blocked. And remember how in the beginning I talked about how SetComp makes it easier to do an allow list versus a deny list. A lot of systems are leaving IOU Ring open by default because of this. And I think now actually the Docker SetComp profile, the default one, allows IOU Ring. And you can imagine there are a lot of reasons to believe that the performance benefits of IOU Ring would want to be utilized for containerized applications. I also mentioned before that Android auto-generates their SetComp policy. So in last I checked, in order to deal with this like security bypass problem, there were talks about having like how to deal with this, and the most mainstream or like accepted idea was having a whole separate IOU Ring security model, which would apply restrictions when an IOU Ring instance is created, but this still doesn't solve the problem if an application can access IOU Ring in itself and create a new IOU Ring instance. And so far, no consensus has really been reached. There's also no LSM hooks on IOU Ring operations themselves. This is not an LSM bypass on the system calls operations, but it still means that all of IOU Ring code is accessible. It's a rapidly growing code base that's getting frequent major refactors and support for probably all system calls is going to be inevitable. And it also means that there's going to be a lot more code that has bugs. And as more devices get upgraded kernels, I think IOU Ring is going to be an important factor in Linux kernel security. Okay, so now I'm going to briefly talk about another bug I found. I think somebody talked about this bug or said that this is a different bug, but this is the one you were talking about. The bug itself is really not important. If you're interested, I have a blog post and I released exploit code, which that's what the guy was referring to. But I want to focus on this talk where in the kernel the code is. So the function you're looking at performs a read-write system call operation in IOU Ring for a certain subset of files. And if you look at the description of the function, you'll see it says for files that don't implement read iter, write iter file operations. So this kind of edge case generality is really ideal in a sandbox escape scenario because for one, it's an odd situation that probably didn't get tested. And at the same time, it's any file that doesn't implement these operations, and a lot of other type of files would also work. I used procfs file in my exploit, and sandbox processes usually have access to that because LSM security context information is stored in procfs. In SELinux, for example, access to the files needed for user space SELinux implementations, but a lot of other files could work to trigger this. So now we have a good idea of like what are good ripe attack surface scenarios. Now you guys probably care about this. How do I actually find bugs? That's a good question. I think syscaller is great. Syscaller is a coverage guided kernel fuzzer. You don't necessarily have to set up your own fuzzer instance even. You can view live bugs that are being found on Sysbot, which Google has their cores fuzzing, and you can see them in action and see live bugs. It's not unusual to just happen across exploitable bugs this way, even though it seems improbable. It certainly happens. The file system bug that I mentioned earlier was found this way and exploited within a couple of weeks of syscaller reporting it, and the reporters got a pretty sizable bounty for it, so it's definitely lucrative. And if you set up an instance yourself, you shouldn't expect to find anything that SysBoss is not finding, because you're probably underpowered in comparison to Google. But there are plenty of opportunities to improve coverage and find your own bugs. Currently, all syscall descriptions are manually written, and there's no fully automated way to generate descriptions, so there are gaps. So you can improve coverage by writing new system call descriptions for kernel interfaces with poor coverage. And the neat thing about syscaller is that it provides a nice coverage KCov report that gives you line-by-line analysis about what code is being hit by the fuzzer. And so there's a lot of opportunity for media drivers or like vendor OEM drivers that aren't being fuzzed in a sandbox contents, and you can still find a nice bug to escalate from a trusted segmented process to kernel. There's also a lot of opportunity for improvement is the syscaller instance finding Linux kernel on NDAs. There's a lot of NDAs exploits, my own included, that syscaller can't currently find. So there's opportunity to find out why and improve your definitions and improve your fuzzing. You can also tweak syscaller instances to work within a sandbox, specific sandbox setup for your target. It currently has support out of the box for like set UID, like DAC and namespaces, but with a little TLC, you can get it to work within a specific SELinux policy, and you probably should use your target if you're targeting a specific device. Looking at NDAs themselves are a really great way to pick both a target, because you can see what the security impact of some of the reported bugs are, which helps you find more bugs. If you watch NDAs, you'll see the same cast of recurring characters. You can see the people that find vulnerabilities and report them, and the different parts of the kernel you know really well as the developers that are committing code to it. And you can definitely learn a lot about a part of the kernel by just looking at what vulnerabilities have been reported and what the attack surface is. And so especially when you're targeting vulnerabilities that have to bypass various sandbox mitigations and hardening measures, it forces you to interact with parts of the kernel that you might not have otherwise done, and you learn how the kernel works really well in that way. And I've definitely found bugs this way. One in particular was an ALU sanitation mechanism in eBPF. I don't have it here because it's not really a sandbox escape bug. eBPF has kind of like been locked down really hard in the past year, probably partially because of the publicity that's gotten for exploitation that I've contributed to. But I didn't realize there was a bug in this ALU sanitation mechanism until I wrote an exploit and thought that it shouldn't have worked, but it actually did. So it was broken. So don't take mitigations at face value. That's a lesson. Okay. And so if you know me well, you will know that I am always talking about this. I'm talking about patch gaps, which this can be a talk totally in itself, but that's not what this is today. But it's one with like a lot of complicated history, so I'll run down the basics about what this means for usable bugs. Linux kernel culture is still very much hostile to security inherently. A bug is a bug, doesn't matter if it's security or not, which leads to obfuscating security-related implications in patch messages or git commit messages. And so a lot of the time, security-related patches are not backported to older kernels, although admittedly they're getting better about that. But older kernels are used by many embedded devices. And I think currently the latest Android phones are like 5.10, so they're catching up, but like everything else is still really far behind. So individual vendors and distros are kind of forced to cherry pick security commits, which is really difficult to do if there's no unified way to identify what is a security patch and what isn't, especially if the commit message is totally obscure, like obfuscated. The official Linux kernel upstream position on this is that they kind of operate in this fantasy world where everyone is going to sync on stable releases and upgrade in a timely manner, but that's not reality. So we've seen this happen often in the wild exploits targeting 0 days, but they've already been patched upstream for years. And NSO is kind of notorious on this, but it's great for offense, so yay. A huge recommendation I'd give if you want to look for kernel bugs that are usable to escape sandboxes or just generally LPE is look at upstream's commit history and like whatever your kernel subsystem target is, and cross-reference those commits to your specific target's kernel. If you have source, run a diff and just see what patches make it in. Everyone that's taken my advice has come back to me with some really entertaining commit messages for some really heinous bugs, and you would be really surprised. So don't take those at face value and just like actually look at the diff and look at the bug that's being patched, because a lot of the times it is exploitable. And finding one of these is a great way to get a really sizable bounty, either via Android, which I think pays better, but also Google's KCTF program, and also evidence by NSO, you could probably sell to a broker if that is your thing. And I'm really sorry I totally rushed through this because of the technical difficulties, but now I'm going to leave time for questions.
Hey, how you doing? Great talk, by the way. Thank you. So, quick question. You said that before you got involved in security, you were looking at economics, right? Or you studied economics.
Yeah.
What inspired you to make that transition?
I really fucking hated economics. I worked at the Federal Reserve in macroeconomic research, and I studied math before that, and I thought it was like a practical way to like apply mathematical theory, and the reality was really disappointing, and I was depressed. So I don't know if that answers your question. Yeah. Alex? Yeah, I think so.
Hey, so I think Google's working on some patches to allow eBPF to do page faults, so you can like read command line parameters and stuff like that. Mm-hmm. Do you think that'll change and make eBPF a better tool for sandboxing, or there'll still be other limitations?
Yeah, that's a good question. I definitely think that. So for the record, the reason why SetComp can't do like pointer dereferencing is because they use classic eBPF. Classic BPF, and eBPF is the like upgraded version of BPF, which can do parameter dereferencing. So for whatever reason, because it's older, or there's some history there that I'm not super familiar with, they use classic BPF that can't do pointer dereferencing. But yes, that would be something helpful for SetComp to have more power, more control in their sandbox to use eBPF. That's like the modern version.
Hey. Until all these bugs are obviously fixed one day, do app developers or Linux developers have a way to harden their own sandbox security, like not allowing access to IOU Ring or any of those more vulnerable interfaces, user namespaces, or any of that?
Yeah, no, of course. I'm always hesitant to give specific hardening recommendations because I don't know, the answer is always dependent on what the use case for your system is. But if it were me, I think not blocking IOU Ring entirely is kind of harsh because I do think it's useful. But yeah, I think it's a question of really doing, the old adage of, only giving access to what's entirely required. And I do think that eventually, like Linux kernel maintainers are going to have to grapple with the IOU Ring security problem. And the suggestions that have been so far of like developing a whole IOU Ring security model seem impractical to me because as we've probably everybody in this room has seen, that takes work and coordination, and so anything that can be more streamlined, so streamlining IOU Ring with SetComp or like other LSMs is ideal. I don't know how practical that is and getting everyone to cooperate in that, but I see that as the best case solution to make security easy for developers and administrators and writers of security policy. No other questions? Thank you so much, guys, for being good sport. I'm so sorry about the difficulties.